Hello friends, in this video we will learn about second moment method that can be used to find reliability of a system. In the last video we have seen how to use concept of safety margin and concept of reliability index to calculate the probability of failure. But those method has some limitations. For example, the calculation of the probability of safety or probability of failure requires the knowledge of distribution function. It can be distribution function for demand, or it can be distribution function for capacity, or it can be joint distribution function fxy. So if you remember, the safety margin M is given as x minus y, where x is the capacity and y is the demand. So this means if I want to calculate safety margin M, I have to know the PDF for x and PDF for y, and also in some cases we have to know the joint probability density function. So this is one disadvantage. Similarly, if I have limited data set, which is the case very often, in those cases, estimation of these PDF functions is not an easy task. Moreover, the exact evaluation of probabilities, that is probability of failure or probability of safety, requires numerical integration, and this is challenging for engineer that is working in the field. Hence, it is important to have a method that is simple enough and can be applied in the field, and we can use this method for calculation of probability of safety or probability of failure. And that's why we often use first and second moment, that is mean and variance of the random variable, to calculate the reliability or probability of failure. So in this case, we don't need to have the PDF function, we need to only know what is the mean and what is the variance of that random variable. And this kind of method is called second order or second moment method for calculation of reliability. This is often called second moment formulation of reliability. Now, for example, if you consider reliability index that is given by beta, that is mu m divided by sigma m, in this case, first moment is mean, that is mu m, and the second moment is variance. If you take a square root of variance, that is basically a standard deviation. So we are only using first moment and the second moment to calculate the reliability index. We don't need to have the probability density function in this case. Now we will see how we can use the concept of second order moment to calculate safety margin. So if you remember, safety margin is given as M is equals to x minus y, where x is the capacity and y is the demand. Now when my capacity is greater than demand, that is x is greater than y, or in other words, x minus y is greater than 0, I can say my system is safe. That is, when we have m is greater than 0, this is x minus y, which is greater than 0, then I will say this is a safe state. Similarly, if m is less than 0, we will call this as a failure state. Now what we will call when m is equals to 0? That is basically by limit state. So let us illustrate these three states using a graph. So we have safety margin M that is equals to x minus y. So let us plot x, that is capacity, on the horizontal axis and y, which is the demand, on the vertical axis. So if you consider term x minus y, so let us consider limiting case, that is limit state, we will have x minus y is equals to 0, or we will have simply y is equals to x. So this is an equation of line passing through origin. So we can plot this. So we will have this line. Now this is my limit state, that is m is equals to 0. Now if you consider a point this side of line, For example, let us consider this point, and for this point, this is the x distance, that is x coordinate, and this is my y distance, that is y coordinate. So you can see in this case x is greater than y. So for all point in this region we will have x is greater than y, that is x minus y is greater than 0. So we will have this side safe region. On the other hand, this side of line we will have m is less than 0, that is failure region. So m is less than 0, so we will have failure region. So basically we have a limiting state, we have safe state, and we have failure state. All this is plotted in this graph. One important point we can say, my demand and capacity is generally positive. So in this kind of graph we are only concerned in the first quadrant. Other quadrants is not that much useful because we cannot have negative demand and we cannot have a negative capacity. So we have written my limit state in terms of variable x and y, that is in terms of demand and capacity. Very often we talk limit state in terms of reduced variable. So limit state in terms of reduced variable. So what we do, we try to normalize the variable. So like this is very similar to normalization of a variable. So we subtract mu and divide by the standard deviation sigma. So I have a variable, I subtract mean of that variable and divide by the standard deviation. For example, in this case, if I want to write a reduced variable for x, so let us say x dash is the reduced variable. So I have to subtract the mean and divide by the standard deviation. Similarly for y, we will have y dash as the reduced variable, and then I have to subtract mean and corresponding I have to divide by the standard deviation. So from these two equations we can also write x and y. So let us write x. So we will have x is equals to this sigma x goes this side. So sigma x multiplied by x dash, and then mu x will come this side. So we will have plus mu x. Similarly I can write y, which is equals to sigma y times y dash plus mu y. Now once I know x and y in terms of the reduced variable, that is x dash and y dash, we can plug into the limit state equation and we can write my limit state equation in terms of the reduced variable. So that is here we have, so we have limit state equation, that is m is equals to x minus y, and now if I plug the value of x, that is written here, that is mu x plus sigma x plus x dash, and if I plug the value of y also, then I get my limiting state equation or limit state equation in terms of the reduced variable. And similar to previous case, we can also show this equation, that is the limit state equation in terms of reduced variable, in a graph. So let us show this. So that is graphical representation of limit state function in terms of reduced variable, and we will assume that mu x, that is mean of capacity, is greater than mean of demand, that is mu y, and that is basically logical. We always try to make a design in which mean of capacity should be greater than mean of demand, so that we can avoid a failure. So at limit state m is equals to 0, so we can write the above equation something like this. So 0 is equals to mu x plus sigma x x dash minus mu y minus sigma y dash. Now let us take this term and this term left hand side. So we will have sigma y dash minus sigma x x dash, and this is equals to mu x minus mu y. We can also write this expression by dash divided by mu x minus mu y, and this divided by sigma y, plus x dash, this divided by mu x minus mu y, and this divided by sigma x, and we have to put a negative sign here, and this is equals to 1. So now this is the equation of a straight line in form of intercepts. So this is the intercept on y-axis and this is the intercept on x-axis. So you see, since mu x is greater than mu y, this term is positive and this term is negative. So we will have a negative intercept on x-axis and positive intercept on y-axis. So let us plot this. So this is my x dash and y dash axis, and this is the limit state line that we will have, and the intercept on the y-axis, that is mu x minus mu y divided by sigma y, this term, and this is the intercept on x-axis, that is a negative intercept, mu x minus mu y divided by sigma x, and this is the limit state equation, that is the limit state line. So this line is limit state line. Now if you consider any point this side, either this, that is this region, basically if you see, this corresponds to m is greater than 0. For example, if you put this point, this is nothing but x dash is equals to 0 and y dash is equals to 0. So if you put this point in this equation, you will see this is 0 and this is 0, these two terms are 0. So you are only left with mu x minus mu y, and since mu x is greater than mu y, so we will have a positive term. So basically any point that lies this side of the line corresponds to m is greater than 0. So that is a safe state. Now similarly, if you consider any point this side of line, that is basically m is less than 0, and that corresponds to failure state. So this graph shows how we can plot limit state in terms of reduced variable x dash and y dash. But now the question is how we calculate reliability in terms of the reduced variable. So the distance from the failure line, that is the limit state line, to the origin is a measure of reliability. So this is what we have in second moment method. So this is saying the distance from origin, shortest distance, to the limit state line is basically measure of reliability. And the limit state line equation is this one. I have to plug this is equals to 0, that is m is equals to 0. In this case, this is the limit state line, and this is the intercept on y-axis, and this is the intercept on x-axis. And this is the shortest distance from origin to the limit state line. Let's call this distance as d. Now the question is how we calculate this distance. So if you remember, we can use a formula that we have already learnt in coordinate geometry. So let's say if I have line equation ax plus by is equals to c, then we have the formula for perpendicular distance p is equals to c divided by a square root of coefficient a square plus b square, and we have to take magnitude of c. Now we can use this formula here. Since m is equals to 0, I can write this equation 0 is equals to mu x minus mu y, and then plus sigma x x dash and minus sigma y dash. So if I take these terms left hand side, I will have sigma y dash minus sigma x x dash, and this is equals to mu x minus mu y. So in my case, the c is mu x minus mu y, and the coefficient a, that is sigma x minus sigma x, and coefficient b is sigma y. So we can write expression for perpendicular distance d. This is equals to coefficient c mu x minus mu y, that is intercept, and this divided by a square root of sigma x whole square plus sigma y whole square. Now the term mu x minus mu y is already positive because mu x is greater than mu y, because we have assumed that mean of capacity is greater than the mean of demand. So D in this case is a measure of reliability. So if I can calculate this term, then we can calculate some measure of reliability. Now we can also derive expression for D using simple geometry. So let's discuss that also using an alternative solution. So we have to calculate this distance D, and the intercepts are given. So this is the intercept on y-axis and this is the intercept on x-axis. So let us consider this triangle A, B and C. Call this angle as theta. So we can write sine theta in triangle ABC. So triangle ABC, I can write expression for sine theta, which is equals to distance D and divided by intercept on x-axis, that is nothing but minus mu x minus mu y, and this divided by sigma x. So this term. Similarly, now this angle is theta, so this angle will 90 minus theta because this is 90 degree, and this angle is theta because this angle is 90 degree. So this angle is theta. So now we can use triangle BCD. So let's write in triangle BCD, I can write expression for cos theta. So cos theta in this triangle will be nothing but D divided by, we have to write intercept, that is mu x minus mu y, and this divided by sigma y. Now we can use identity, that is sin square theta plus cos square theta is equals to 1. This means the square of this term plus the square of this term is equals to 1. So let's write that. We will have ds square divided by mu x minus mu y, and negative becomes positive and sigma x term goes on the top. Similarly here I can write ds square sigma by square mu x minus mu y whole square, this is equals to 1. So from here I can write ds square is nothing but mu x minus mu y whole square, and this divided by sigma x square plus sigma y square. So this means this distance D is nothing but D is equals to mu x minus mu y, and then divided by a square root of sigma x square plus sigma y square. And this is same as we derived earlier. So now we can see the distance from origin to the limit state line is somehow a measure of reliability. In fact, in some special cases, this distance becomes equals to the reliability index. For example, if my x and y are normal random variable and they are independent, then this distance D is equals to the reliability index beta. So distance D is equals to beta. And if you remember, we can calculate reliability index beta using this formula, that is mean of safety margin M divided by a standard deviation of safety margin M. So we can write safety margin M is equals to capacity X minus demand by. Now in this case, X is normally distributed, Y is normally distributed. So it can be shown that M is also normally distributed. And then we can find mean of M, which is equals to mean of X minus mean of Y. Similarly, we can calculate mean of basically a standard deviation of safety margin M, and this is equals to a square root of sigma x square plus sigma y square. Now in this case we are assuming that these two terms are independent, that x and y are independent, and that's why covariance term will be 0. So now if I plug this value in this expression, I will get expression for beta, which is mu x minus mu y divided by a square root of sigma x square plus sigma y square. And this is same as the distance as we calculated previously. So you see, in this case, distance d is equals to reliability index beta. So what we can say here is distance d is somehow a measure of reliability. In a special case, this becomes reliability index. So to summarize, in this video we have seen how we can write expression for safety margin and how we can convert that expression in terms of reduced variable and how to calculate distance from origin to limit state line, or this can also be a surface if I have multiple random variables. In the next video we will see how we can calculate this distance, that is a measure of reliability, if I have a multiple random variable function. So we can stop here and see you in the next video. Thank you.